All right, hello everybody. Today we are going over the third lesson of Unit 2, which is on structure of ionic solids. Your understanding today is that the cations and anions in an ionic crystal are arranged in a systematic periodic 3D array that is going to maximize the attractive forces and minimize the repulsive forces. Your objective is to represent an ionic solid with a particulate model that is consistent with Coulomb's law and the properties of the constituent ions. Ionic interactions produce brittle, hard solids in the form of crystal lattices. This 3D array of atoms is going to be a result of the ions being attracted to their opposite charges. So for example, in this figure on the right here, we have our sodium cations and our chlorine anions. Each cation will be surrounded by anions, and each anion will be surrounded by cations. So they form this way to maximize the attraction between the cation and the anion and minimize the repulsion. So there's no cations next to each other and no anions next to each other, or else they would repel. So in the previous slide, we talked about ionic solids being brittle, and I wanted to go over explicitly what that meant. So brittle is essentially something being hard but easily broken. And the reason ionic solids are brittle is because when you apply a force like hammering or scratching or something to an ionic solid, the layers of the ions can shift. And if the shift brings like charges next to each other, then the electrostatic repulsion is extremely strong. So that repulsion is then going to cause the lattice to shatter along a plane, which is where we get those crystal cracks or brittleness. And before we do some practice problems with 2.3, I wanted to remind you that if you are ever comparing substances and you want to compare electronegativity, ionization energy, or atomic radius, please remember that you are not allowed to say just because it's a trend. If you answer the question with because it's a trend, you will get it wrong. You need to know why it's a trend and you need to explain it. So for electronegativity, you're not saying it increases because it's closer to fluorine, or you're not saying it increases because it's more to the right on the periodic table. You have to say electronegativity increases because as you increase the nuclear charge, the attraction of those bonding electrons is going to increase. So you have to give a reason why the electronegativity is increasing, not just because it's a trend or because of where it is on the periodic table. And then with ionization energy, remember ionization energy is the energy required to remove a valence electron. So it's going to increase as you move to the right because as you increase the nuclear charge, you are increasing the attractive force between that positive nucleus and the valence electrons. And because that is now a stronger hold between the two, it's going to require more energy to remove it. And then with atomic radius, that's going to decrease as you move to the right along a period because as you move to the right, you are increasing nuclear charge, which means the nucleus is pulling those electrons closer to the nucleus, making the atomic radius smaller. All right, so now let's take some of that information we just went over and relate it to Coulomb's law. So we've seen Coulomb's law several times already, and we're only in Unit 2. Get used to it. It comes up a lot because it is an important relationship. So force is directly proportional to charge. So as you increase your charge, you are also going to increase the force, whether that be repulsive or attractive. If we are looking at two compounds, sodium chloride and magnesium oxide, which has a higher force and is it attractive or repulsive? So if we're looking at sodium chloride and magnesium oxide, there is an obvious charge difference between the two. Sodium has a positive 1 charge, chlorine has a negative 1 charge, magnesium has a positive 2 charge, and oxygen has a negative 2 charge. Well, looking at this, I hope you understand that magnesium and oxygen have much greater charges than sodium and chlorine. So you would know that magnesium oxide had a higher force. However, if you would like to plug it in to Coulomb's law, just looking at the numerator for charge, you can totally do that so you can understand where this comes from. So for example, if we were just looking at charge, which is the numerator of Coulomb's law, for sodium chloride, we would have a positive 1 charge times a negative 1 charge, which gives us an overall product of charges of negative 1. Then if we were doing magnesium and oxygen, that would be plus 2 times negative 2 gives us negative 4. So obviously we have a lot more charge with magnesium oxide. And remember, in Unit 1, we talked about Coulomb's law. If we have a negative number for our force, that's going to be attractive. And that's just because we have a positive and a negative, which means they're attracting to each other. If we were multiplying positive times positive, that would give us a positive. If we were multiplying negative times negative, that would also give us a positive. So if the number comes out negative, we automatically know it would be attractive forces because you have to have one of each charge, and that would make it negative. And the next part of Coulomb's law is distance. So force is indirectly proportional to distance, which means as your distance decreases, the force between the two particles increases because they're closer together. So just keep in mind the smaller particles and the shorter bond lengths are going to give you a higher force because they are closer together and it's harder to take them apart. So if we're looking at two compounds, magnesium chloride and calcium bromide, which would have a greater force? So first, looking at the charges, we know magnesium is a +2, calcium is also a +2, and each one of these chlorines is a -1, and each one of these bromines is a -1. So the charges are the same in both, so we need to look at distance between the ions. Now looking at your periodic table, you can see that magnesium is in the 3rd energy level, and when it becomes a cation, it actually has 2 occupied energy levels because it donated those 2 electrons in the 3rd energy level. And for calcium, it started as a neutral atom with 4 occupied energy levels, but when it became an ion, it went down to 3 because it donated those 2 electrons. So calcium is larger than magnesium, which means if we were looking at the compound with a greater force, we want to look for the smaller ion. And since both of the anions are the same, we're looking at the cation. And since magnesium is a smaller ion, it would have a greater force between the magnesium and the chlorines. So your answer here would be MgCl2. All right, so let's introduce a new term for you, something called lattice energy. So lattice energy is the energy change that occurs when a mole of an ionic solid is separated into its gaseous ions. Now think about it. If we have an ionic solid and you want to determine the energy required to turn it into gaseous ions, you have to think if it has a tighter or stronger bond, it's going to take more energy to break it apart. So if we're looking at 2 ionic solids of rubidium chloride and sodium chloride, we can see that both of them have chlorine. So we're specifically looking at the difference between sodium and rubidium. Now, if we're looking for a stronger bond, remember we're looking at Coulomb's law, the first thing we need to look at is charge. Well, they're both in group 1, which means when they became ions, they both donated 1 electron, which means they have a positive 1 charge. So we're not looking at charge, we're looking at distance. Now you can see sodium is much smaller than rubidium, which means the electrostatic force between sodium and chlorine is much stronger than between rubidium and chlorine. All right, so let's do another practice problem. The energy required to separate the ions in magnesium hydroxide into individual ions is known as the lattice energy of magnesium hydroxide. As shown in the table, the lattice energy of strontium hydroxide is less than the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties and Coulomb's law. So we can see in both compounds, we have a 2+ cation. So we're specifically looking at distance here because all of our ion charges are the same in both compounds. So looking at magnesium and strontium on the periodic table, we can see that magnesium is much smaller because it's only going to have 2 occupied energy levels. And what I mean by that is if you look at magnesium, magnesium has 3 occupied energy levels at the start of this. However, when it becomes a cation and loses its 2 outermost electrons, it goes back down to the second energy level. So it only has 2 occupied energy levels, whereas strontium has 4 occupied energy levels. So because magnesium is so much smaller than strontium, it's going to have a greater Coulombic attraction between the magnesium and the hydroxides. And since that attraction is greater, it's going to require more energy to break it up into its individual ions. All right, so let's check your understanding so far. So it says write the complete ground state configuration for magnesium 2+ and strontium 2+. Now remember, ground state just means all of your electrons where they're supposed to be. None of them are excited and moving to higher energy levels. So ground state electron configuration is regular electron configuration. Remember, with AP chemistry, you can do the full electron configuration or you can do the noble gas if they did not specify otherwise. So looking at magnesium 2+, we started with normal magnesium, but then we lost 2 electrons. So now we are isoelectronic with neon. So we're going to do the electron configuration as we would if we were doing the electron configuration for neon. So that means either starting with 1s2 or with helium in brackets, doesn't matter, then going to 2s2, and then ending in 2p6. Again, you could also do helium in brackets, 2s2, 2p6, both of them would give you the correct answer. So now let's do the same thing with our strontium 2+ ion. So strontium is here. If we were to lose 2 electrons, that means we would have the same electron configuration as krypton or isoelectronic as krypton. Remember, you can't just do this and call it a day. You have to go to the previous noble gas. So we are going to argon. And then we're going to start from there. So we have 4s2. Remember, the D sublevel starts at 3, so 3d10, and then 4p6. And that would be our electron configuration for the strontium 2+ ion. The next question says, do you predict that the ionic radius of the strontium ion is larger or smaller in size than the ionic radius of the magnesium ion? Justify in terms of atomic structure and electron configuration. So you should know just from that electron configuration we just did that strontium has electrons occupying the 4th energy level, where the magnesium ion only has electrons in the 2nd energy level. So the strontium ion is going to be much larger because it has 2 extra occupied energy shells beyond what magnesium has. Then the last question says the lattice energy of magnesium chloride is equal to 2300 kilojoules per mole. Do you predict the lattice energy of strontium chloride less than or greater than 2300 kilojoules per mole? Justify it in terms of Coulomb's law. Now, we know that magnesium is a smaller ion than strontium. We know that the bond between magnesium and chlorine is going to be stronger than the bond between strontium and chlorine. And since the bond is stronger, it's going to take more energy to break that bond. So because it's going to take more energy to break the bond of magnesium chloride, that means the lattice energy of strontium chloride is going to be less than that of magnesium chloride. All right, to close out this video, let's go over a previous FRQ given on 2.3. It says the student finds the following particulate model of AgCl. Assuming the crystal structures are similar, how should the student modify the model to represent AgBr? So both of the ionic solids have silver in the compound, so we're specifically looking for chlorine and bromine. Now, chlorine and bromine are both halogens that form a -1 charge. However, bromine is going to be larger because bromine has electrons in 4 energy levels, while chlorine only has electrons in 3 energy levels. So because bromine has more energy levels or electron shells, it's going to be a larger radius. So if you were to redraw this for AgBr, it's going to look very similar. It's just in place of the chlorine ions are going to be slightly larger bromine ions. Now, part F of this long FRQ was only worth 1 mark, and if you wanted to get that 1 mark, you had to have 2 specific things in your answer. The first thing is you had to say that bromine ion was larger. So we said that the bromine ion is larger. The next thing you had to say is that it was larger because it occupied more energy levels. So in the second part of our response here, we said this is because the bromine ion has energy levels occupied up to the 4th energy level instead of chlorine that only occupies 3. Okay, I hope that video helped. If you have any questions, please feel free to ask. I hope you have a great day. Bye.